Okay, thanks for the introduction. My name is Yihe from National University of Singapore, and today I would like to present joint work done by me and Gregory on persistent iterators with value semantics. The main idea of our work is to bridge two seemingly incompatible program paradigms, persistent data structures, and iterator-based programming. To set the stage, let's first establish what we mean exactly by persistence. To simply put, persistence just means that objects are never mutated after their creation. For example, take the classical example of creating a widget. When we create it on some coordinates and then draw it, afterwards we create a reference to it and then modify it in place. This is not persistence because modification done on W is in place, and it will also modify V, of course. And that's just a remote in-place modification that is the source of many aliasing hazards. Instead of this, let's imagine a persistent world where we are not allowed to mutate an object after its creation. In this world, we see that we can only rebind the widget to another value instead of modifying in place, and rebinding it will not affect V at all. There are some other advantages of persistence, such as avoiding spooky remote in-place modification, and such on above. There are no side effects possible when we call a function, and also it allows for better optimization because there are no aliasing possible. Due to these advantages, in 2026, there is actually a trend to introduce persistence in many popular languages, libraries, and systems, such as Immer, functional programming languages, and Verse. So why is that? As I shown before, there are many advantages such as safety, predictability, and arguably better ergonomics. Of course, there's also some disadvantages of introducing persistence, that is different abstraction. In classical persistence languages, they use a fundamentally different abstraction. For example, in functional programming languages who are more familiar with combinators and recursion, instead of loops and iterators that are more familiar to traditional languages programmers. This is good in its own, but we must admit that objectively, these abstractions appear rare due to the relatively low adoption of functional programming languages, and this constitutes a great obstacle of adopting persistence in many traditional programmers simply because they are not familiar with this kind of abstractions. And this is exactly what our work set out to do. We want persistence without changing the abstraction to bring familiarity to ordinary programmers. Our work, persistence iterator with value semantics, basically want to bring persistence while retaining the familiar abstractions. To further illustrate how that works, let's look at a concrete example. Suppose we want to filter the unwanted elements from a bag of elements. For example, we want to remove all the colors from this bag of colors that are surrounded by brackets like this. So how can we implement this with imperative programming languages, and how can we implement this with functional programming languages? It turns out that the solution in both paradigms are very different and inspiring. Let's first look at an imperative programming solution. This is an example solution in C++ that uses step-by-step reasoning with familiar constructs such as loops, variables, and iterators. In this solution, we can see the familiar iterator abstraction used to iterate through the collection. We can also see explicit state management done by the variable want. We can also see how exactly this solution works. So in one iteration, if we want to retain the color, the iterator will just move to the next element. However, if we want to remove the color from the collection, we call erase on the collection, and that will return actually the next element after the remove element, and this will also move iterator to the next element. In this case, we no longer need to increment the iterator itself to avoid skipping over some other elements in the collection. However, the solution is not really persistence, because iterators in C++ are generally references of positions instead of standalone values. And also, this is directly modifying the data structure. We are calling erase on it in place, and we are violating the no modification of the creation rule. So in conclusion, iterators in traditional languages are seemingly not persistent, as they are mutable references inside of containers. This also brings with it some safety hazards directly due to the lack of persistency. For example, this is firstly a slightly awkward API design. We must rely on the erase method returning the next iterator position. And this is also easy to get wrong and suffer from iterator invalidation hazards. For example, an easy mistake made by many beginner or even advanced programmers is to just not capture the return value of the erase method and instead just leave it here. In this case, we see on the bottom that the iterator will be still pointing to the remove element. And in the next iteration, when we try to dereference it, it will be a use after free hazards. Similar hazards like this are the direct reasoning why we want to introduce persistence in traditional languages. Now let's look at how functional programming solves the same problem. FP languages like Haskell avoid such problems because all data structures are assumed to be persistent in there. So in this example solution shown here, we can see that there are no modification, only composition here, and persistence is enforced everywhere. This is obviously good. However, the Haskell solution also have its own problems. So it relies on combinators, specifically two-pass combinator, because there are no built-in support for step-by-step modification. We must rely on reverse. This is a completely different abstraction compared to the previous solution, which incurs loop and iterators, and this is unfamiliar to many programmers. So this is where our work comes in. We want to answer the core question: is persistence and iterator fundamentally incompatible? Well, if we look at this solution, we can see that seemingly yes, because we are trying to modify the container in place, and iterator references position, not value. However, this can be changed if we give iterator value semantics. In fact, by giving iterator value semantics, we can imagine in that world, each iterator will now hold its own snapshot of the container. So when we call erase on the iterator, it will be pointing to a new snapshot of a new container that doesn't contain this element. And the original container will be intact because we are only modifying a snapshot. By following this reasoning, we can see that persistence is actually only incompatible with reference semantics, not the iterator abstraction itself. Now, this is how the STL iterator works, and this is how the new code in our library works. So we can see that to achieve persistent iterators, we only need to change reference semantics to value semantics and introduce a few syntax modification. For example, while we are still using iterator to iterate through the container, we now call erase directly on the iterator because we want to modify the snapshot, not the container itself. Also, we need to materialize the snapshot back into its own container at the end, because after the loop, the original container will still not be modified, and if we don't materialize it, the whole loop will will have no effect after all. You may wonder if this is inefficient. After all, in each iteration, we are creating new snapshot of the middle states and with partial element removal, and that may be inefficient in a traditional sense because you may imagine it is copying all the elements. But by carefully designing the data structure, we can show that this is not actually inefficient. In fact, we implement our common containers in our library with a single unifying underlying data structure called finger tree. It's basically a complexly modified version of the binary search tree that allows amortized O1 access to ends, which is ideal for things like vectors and other sequence containers because they generally rely on very efficient access to both ends. Also, this is obviously very suitable for sets too, because sets are just implemented as trees in most languages too. Furthermore, iterators are now realized as zippers on the trees, which just means that it keeps track of all the nodes from itself to the root and all the intermediate nodes. When we try to add or remove elements through an iterator as shown on the bottom left, we can see that we only need to recreate the subtree that contains a modified segment and can reuse most of the intermediate nodes up until the root. This makes copying very efficient. In fact, it makes copying amortized constant, which solves the efficiency problem. In fact, by carefully went through all the algorithm complexity and comparing them to the standard library ones, we can see that in the majority of cases, container operations actually have the same or better complexity when compared to their STL counterparts. In the image shown on the left, the yellow blocks show the case where the time complexity is the same, and the green parts show where the complexity of our library is actually better. Of course, there's no free lunch, and there exists some unavoidable trade-off in some operations just due to the limitation of tree structure. But in general, we think that at most it's a logarithmic time slowdown, and that is very worth it when we treat them for the various advantages of introducing persistence. We also done some micro benchmark results on our newly introduced persistent containers and compare them to both the standard library and several third-party popular libraries in C++, such as Upsil and foldl. We can see that persistent containers does have a large constant factor than popular libraries. For example, in vectors, it's hard to beat just a sequence read, just due to indirections and tree transversal costs. However, in some cases, we can see that our library actually has an algorithmic efficiency, and in most cases incurring sets operations, we can see that our library performs comparatively well compared to other third-party libraries and the STL. We also done some benchmark results on using iterator operations instead. We can see that the persistent iterators are low constant time update erasure, but with similar constant factor overhead as using the containers themselves. We can see that this graph is very similar to the ones in the previous slide, showing that they basically have the same performance characteristics. Finally, we also benchmark the memory usage of our library compared to common third-party libraries. Our implementation use reference counting, so all the intermediate states that are no longer referenced will automatically be collected. As such, our containers or iterators exhibit comparable memory usage patterns compared to most popular libraries. So you can see that the green line showing our library is very similar in characteristics to other libraries. So in conclusion, our library has shown that persistence is in fact compatible with many familiar idioms in traditional languages such as loops and iterators, as long as we just get rid of reference semantics and embrace value semantics. Our library tries to be safety by design and introduce a better ergonomics by introducing persistence without changing the familiar APIs. And we also show that our library has comparable performance and competitive complexity compared to major libraries across all the third-party or the standard library. So you can scan the QR code for more information on our library, and thank you for listening. That's all.
Thank you for the talk. We have 5 minutes for Q&A.
Thank you. Very interesting work. I was just wondering how hard it is to get from the current code, the current iterator code, to your new iterator model. Did you inspect that?
Okay, yeah, so that is a very good question. And it's actually, even though it's pretty familiar API, it's still a paradigm shift. So so when we move from traditional iterator to our code, it's not a trivial task. But we have used our iterator library internally in many large projects, and we would say that using it to develop has roughly the same complexity as using the standard library. So I ultimately don't think that change to this, our library will incur a very high mental cost or anything like that.
Hi, thanks for the great talk. I have two sort of related questions about like sort of, I guess, different directions for benchmarking this. The first is, have you tried any small finger tree optimization sort of things to offset the large constant factors for the implementation? And second of all, obviously this is not an efficient idea, but I'm curious, like, if you were to implement reference semantics naively with like traditional looking data structures, how bad of a slowdown do you get? How much are you improving upon by bringing value semantics to like a more naive implementation that uses,
Yeah, that is two actually very good points. We have actually think about using small finger tree optimization, but ultimately we didn't really pursue that case as there's a bit of implementation difficulty. But we definitely try to bring it to fruition in future work. Also, we try to optimize the performance of allocating so much small objects by changing to a slab allocator anyway. So we don't think that using that optimization will change the performance characteristics very much. As for using traditional libraries with reference semantics, I believe that if we try that, we need some like major solution that is accepted by industry to make our comparison more like convincing and things like that. So we haven't actually done that yet, but thank you. We will definitely consider this in a future comparison.
Thank you very much.
Does this work with iterator insertion as well?
Yeah, it does. In fact, in the finger tree diagram, we have actually shown how insertion works, not erasure, but they work similarly.
It's pretty cool. Thank you.
Any more questions from the audience?
Very interesting work. Thank you for a very good talk. I was just curious, and this is going back to the first question. Conor McBride had this idea of these zipper-like structures can be obtained by differentiation. So could you take traditional implementations and just apply a derivative-like operation on all of them in order to get your persistent iterator structures?
Yeah, maybe I believe it will be possible, but either way, it will require extensive modification of those traditional libraries too. So I think it will be better if
you could probably make a parallel set of equivalent libraries.
Yeah, it makes sense, and we will consider it and maybe compare to such an implementation in the future, I believe.
Thank you.
Let me have one final quick question. So would you please summarize the characteristics of the usage cases where people should choose your persistent iterator over the mutable iterators? Or how would the developers make the most informed decision on which type of iterator to use in their own programs?
Okay, that is a pretty good question. I believe that the main choosing criteria probably would be based on how much you value the advantage of persistence, such as how much you want to avoid aliasing or how troubled are you in real work with those kind of remote modification and things like that. So if you are a really advanced C++ or other language programmer and you don't really care about those and you can write correct programs, I believe you don't need to switch to this anyway. And maybe it's more tailored towards like a middle field or beginner towards project for something like this.
Okay, thank you. Yeah, let's thank our speaker again. With that, this will conclude this session, and thank you for attending, and I hope you will